Okay, so I'm going to go over the U sub daily grade number 1. There's a clean copy in the Google Classroom. If you want to redo it, remember this goes in your solution manual, so this will be a nice follow along for the solution manual. In addition, I will be posting the just the work in a PDF format. Okay, so we have the integral of x times sine of x squared. So we really only have two things that you can be, either x, well, three things, I guess, sine of x squared or x squared. The problem here is if I let it be sine of x squared, then I need the derivative of that, which is going to be a chain rule issue of the derivative of sine, which is cosine, and then the derivative of the inside, which is 2x, which I don't have. Okay, so that leads me to let u be x squared because I have du if I let u be x squared. So du is 2x dx. So really all I need in here is a 2, and I can do that by keeping everything balanced by adding that 1/2 on the outside. So then I have u and I have du. So this gives me 1/2 the integral of sine of u, and then my 2x dx becomes my du. Okay, now I can take the integral. So I have 1/2. The antiderivative of sine of a positive sine would be a negative cosine. And don't forget, if it has no bounds, we always have to put plus c. And then we need to go back to our original. So 1/2, I'm going to put my negative out front, cosine of x squared plus c. Number 2, it's really only one thing to let u be. So we're going to let u equal 3x minus 2, and then du would just be 3 dx. Now I can make that happen by putting the 1/3 on the outside. So I have 3x minus 2 to the 20th, 3 dx, which is what I need for du. So then I can make my substitution, the integral of u to the 20th, and then 3x dx becomes du. Then we do normal exponential rules, power rules. So u to the 21 divided by 21 plus c. And then I need to simplify and sub my x back in. So I'm going to go ahead and sub my x back in. So 3x minus 2 to the 21st. 21 times 3 is 63 plus c. Number 3, again, we have two things that you can be. It can either be x plus 1 or 2x plus x squared. Now we know from our kind of general rules, we're not going to call them blanket rules or all the time rules, but generally if you have something under a radical, that's probably going to be u. Also, whatever the higher power is probably going to be u, because when we take the derivative, the du of this, we know it's going to drop us by a power. So I'm going to let u be 2x plus x squared, which means my du would be 2 plus 2x dx, which is what I have here. It just needs a factor of 2. So if I'm going to put in a factor of 2, then I need to take out a factor of 2. So I'm going to multiply by 1/2, and then this is going to give me the square root of 2x plus x squared. I'm going to put in that factor of 2, so 2x plus 2 dx. So I have my u, I have my du, and I can substitute. So I have 1/2 the integral of u, and I'm going to go ahead and change this to exponential because it has to be exponential for us to take the derivative. And then this whole thing becomes du. So then we do our power rule. So we add 1. So u to the 3/2 divided by 3/2 plus c. Multiply by the reciprocal, we get 3/4. Sub my x back in, 2x plus x squared to the 3/2 plus c. No, that's not 3/4. So it'd be 1/2 times 2 over 3 sorry about that. I'm trying to rush, so the 2's cancel out and leave me with 1/3. Okay. Number 4, we have cosine theta times sine to the 4th theta. Again, that higher power should be a trigger, and we know that cosine is the derivative of sine. So I'm going to let u be sine theta, which makes du cosine theta d theta. So I don't really have to add anything in. Everything's there just like it needs to be. So I have the derivative u to the 4th, and then cosine d theta becomes du. So then we just use general power rule, add 1 divided by the power. So then we need to sub in our theta. So I have sine to the 5th over 5 plus c. Okay. All right, so let's look at number 5. Okay, so again, we kind of have that same thing. We have a radical and we have a higher power. So it's very likely that that's going to be our u. So I'm going to let u equal 1 plus c cubed, which means du is 3z squared dz. Convenient because we have the z squared, so all I need is a 3. So if I'm going to add in a 3, then I have to take out a 3, which means divide by 1/3 or multiply by 1/3. So then I have 3z squared over the cube root of 1 plus c cubed dz. So I have 1/3 the integral of 1 over u to the 1/3. Just change it to radical form. Du, so the 3z squared times dz becomes du. So I have 1/3 u to the negative 1/3. So then we use power rule. So I'm going to add 1, which gives me 2/3 divided by 2/3 plus c. And then multiply by the reciprocal, and that gives me 1/2. And then my u was 1 plus c cubed to the 2/3 plus c. Make sure that you don't like distribute that and make it like 1 plus z squared, because that's not how that works. Remember, it's not distributive property. Number 6. So we have a couple options here. You could let u be secant, and then the derivative would be secant tangent, but then you'd still have an extra power of secant left, which is a problem. You could let u be tangent, and that's what I said, and you would have secant squared, but you would have a factor of secant. So that would mean that I'm going to have to break this apart into something a little bit different. If you look at this as secant times, or secant squared times secant x tan x, you can see that if you let u be secant, then I have the derivative, because the derivative of secant is secant times tangent. So I'm going to let u be secant, which means du is secant x tan x dx. So I can make a straight substitution. So this would be u squared times du. So I have u to the 3rd divided by 3 plus c, which gives me, when I sub back in, secant cubed divided by 3 plus c. Number 7, again, we kind of have a little problem here, because the two things that we kind of stick to is if it's under a radical, it's probably u. If you have a higher power, that's probably u. Well, this time my higher power is not under my radical. So then it becomes a choice of, well, what do I let u be? So we know if we let u be x, or even x squared, that doesn't help us at all. But if we let u be 2 plus x, I have du because du would just be dx. But I can also still solve for this x, because I know if u is equal to 2 plus x, then x is equal to u minus 2. And then in that way, I can get the entire problem in terms of u. So I have the integral. So x becomes u minus 2, quantity squared. And then 2 plus x becomes u, so that would be u to the 1/2. And then dx becomes du. So then it's still not something that we can really take the derivative of just yet. We need to expand. So I have the integral. So remember, when we square a binomial, there's that shortcut: square the first term, twice the product, square the last term. Okay, and then I can just do distributive property. So u squared times u, remember when we multiply like bases, we add. So it would be 5 over 2 minus 4 u to the 3 over 2 plus 4 u to the 1/2 times du. So then it's just power rule. So add 1, 2 over 2, and divide. Add 1, 2 over 2, and divide. Add 1, and divide. And then don't forget your c, because it's an indefinite integral. So I have 2 over 7. My u is 2 plus x. So I have 2 plus x to the 7 over 2 plus 8 over 5. 2 plus x to the 5 over 2 plus 8 over 3. 2 plus x to the 3 over 2, 3, plus c. Okay, so number 8, we have two things that you can be: x squared plus 1 or x cubed plus 3x to the 4th. So not necessarily to the 4th, but probably just the x cubed plus 3x. So again, typically if you have a higher power in your binomial or in your polynomial, that's probably the one that's going to be u. So let's try it. So we have u is x cubed plus 3x, which means that du would be 3x squared plus 3 dx, which is convenient because that's what this is. It just needs a factor of 3. So if I'm going to put in a multiply by 3, then I have to also take out a multiply by 3, which is a multiply by 1/3. And then I'm going to multiply by 3. So now I'm set up to do my substitution. So I have 1/3 integral of u to the 4th, and then this whole thing becomes du. So then it's just power rule, u to the 5th divided by 5 plus c. So remember, u is x cubed plus 3x to the 5th all over 15 plus c. So number 9. So I could let u be secant, okay, and then I would have u squared. But if I let u be secant, then I would have to have a factor of secant and tangent, which means I would have 2 extra factors of tangent, so I can't do that. So then I could let u be tangent, and then my du would be secant squared, which is exactly what I have. So that must be it. So I'm going to let u be tangent, which means du would be secant squared dx, which means I have the integral of u cubed du. So I have u to the 4th over 4 plus c, and sub back in. So I have tan to the 4th over 4 plus c. Number 10, so this is a definite integral. So a couple things have to happen. We have to decide what u is, make our substitution, and we also have to find our new bounds. Remember, you cannot put the old bounds. Once you've subbed in a u, you've got to have new bounds. You cannot have the same bounds even in a step. Even if you change them in the next step, that's mathematically incorrect. So just be cautious. So we're going to let u, again, we have that higher power. So 1 plus 2x cubed. So du is 6x squared. So clearly we have the x squared. We just need a factor of 6. So if I multiply by 6, I got to take out a 6. So 0 to 1. 1 plus 2x cubed to the 5th. 6x squared dx. So before I even go to the next step, I'm going to go ahead and figure out what my new bounds are because they have to be written in the next step. So when x is 0, which is my lower bound, u would be 1 plus 2 times 0 cubed. So u would be 1. When x is 1, which is my upper bound, u would be 1 plus 2 times 1 cubed, which means u would be 3. So that gives me 1/6 with my new bounds of 1 to 3, u to the 5th, du. So I have 1/6 times u to the 6 over 6, evaluated from 1 to 3. Now if it was me, I would take the 6 out, the 1/6 out, because it just makes the computation easier. So I would do 1 over 36 times u to the 6th, evaluated from 1 to 3. So I have 1 over 36, 3 to the 6th minus 1 to the 6th. So 1 over 36. 3 to the 6th is 729. 1 to the 6th is 1. So you get 728 over 36, which reduces to 182 over 9. Okay, number 11, same thing. So I have to make my u sub, and then I have to figure out my new bounds. So I'm obviously going to let u be x squared, because I can take the antiderivative of cosine, but I can't take the antiderivative of cosine x squared. So then du is 2x dx. So again, if I'm going to add in a multiply by 2, I have to take out a divide by 2. So I'm going to put in my multiply by 2 and my divide by 2. So I'm ready to make my substitution. However, before I do that, I'm going to figure out what my new bounds are. So I'm going to start with my lower bound. So if x is 0, u is 0 squared, which is 0. If x is the square root of pi, then u is the square root of pi squared, which means u is just pi. So my new bounds would be from 0 to pi of cosine u du. So then we take our antiderivative. The antiderivative of of cosine u is sine u, evaluated from 0 to pi. So I have 1/2 sine of pi minus sine of 0. So 1/2. So when you have a trig function involved, sometimes that 0 can get you in trouble. because you think, oh, it's 0. Now, in this case, it does happen to be 0, but if it had been cosine or some other trig function, it may not have been 0. So be super cautious that just because you're subbing in 0, you don't automatically assume that it is 0. However, sine of pi is 0, and cosine of, or sine of 0 is also 0, which gives me 0. So remember, sine is y. This is 0. This is pi. So this is 1, 0. And this is negative 1, 0. So sine is the y value. So I didn't go up or down any. And number 12. Really only one thing to let u be. And that's that argument of t over 4. So du would be 1/4 dt. So this is a little bit different, and it may kind of trip you up, because if I have to put in a 1/4, then I have to multiply by 4 on the outside. So 0 to pi secant squared t over 4 times 1/4 dt. And the only reason I say that would trip you up is not because it's difficult, it's just opposite of what we're used to doing. So we're used to adding in that constant and multiplying by a fraction, and it's kind of flip-flop this time. So just be cautious. So again, before I go to the next step, I'm going to figure out what my bounds are. So when x is 0, u is 0 over 4, which is 0. And when x is pi, u would be pi over 4. Okay, so we have 4 times 0 to pi over 4 of secant squared u du. So we have 4 times the antiderivative of secant squared is tangent, evaluated from 0 to pi over 4. So we have 4 times tangent of pi over 4 minus tangent of 0. 4. So remember, at pi over 4, which is your middle finger, cosine and sine have the same exact value, square root of 2 over 2. So anything over itself is 1. Tangent of 0 is equivalent to sine of 0 over cosine of 0. So you have 4 times 1 minus sine of 0 is 0. So 0 divided by 1 is 0. So you just get 4. Okay, number 13. So I'm going to let u be what's under the radical, which is, there's a lot happening, right? So it may help you see this a little bit better if you write it as a single fraction, so 1 plus 2x to the 2 over 3. So I would let that be 1 plus 2x, which means du would just be 2 dx. So again, if I need a 2 in here, I need to put a 1/2 on the outside. So before I write the next step, I'm going to see what my bounds are. So that's my lower bound, which means u would be 1 plus 2 times 0, which means u is 1. When x is 13, u would be 1 plus 2 times 13, which would be 27. Okay, so we have then 1/2. My new bounds, 1 to 27. This becomes du, and I have 1 over u to the 2/3 du. So I'm going to fix that to something I can take the antiderivative of, so I'm going to move it to the top. Then we use power rule. Add 1, divide by the power, so negative 2/3 plus 3 over 3 is a positive 1/3. From 1 to 27, we have 1/2, 27 to the 1/3 minus 1 to the 1/3. So I have 1/2, 3 minus 1, which gives me oh, I forgot to divide by my 1/3, which means this is a 3 over 2. So 3 over 2 times 2 is just 3.